This conference will now be recorded.
I can't share my screen yet, unfortunately. There we go. Right. One, let me start up. There we go. Right. Just want to check that people can hear me, people can see my presentation before I start. There's no point in me talking to an empty screen. Everyone see that okay?
All good here.
Yeah,
Bill.
good, Phil. Yeah.
Fab. Okie dokie. Right, so welcome. Acton Diveunder. Now, this was a project I did a few years ago. It's something that I spent a good few years doing, quite enjoyed myself. At the time, I was a project engineer for Track, so just a brief introduction to who I am, really. For Acton Diveunder, it was September 2013 until May 2016, so a few years back now, but it's still fairly fresh in my memory. Still quite an interesting project to hear about. I currently work on the South Wales Electrification as a senior project engineer Track. I'm also a part-time lecturer at Coventry University. I teach railway track engineering up at Coventry University. Before that, I was various Crossrail bits and a track designer up at Scott Wilson Railways. So, things I'll cover in Acton Diveunder. Project itself, design the slab track. You can read bullet points. That's what I'll go through in the presentation. Hopefully, spend a good hour entertaining you. So, what is Acton Yard? What is the project? This is the final layout. This is what it looked like at the end of the project. Acton Freight Yard is a few miles out of London Paddington. It's on the relief line side. So Paddington sort of off this junction. These two lines here go up towards the North London line. They diverge and go up north. These four lines here go into London Paddington. This is Acton Freight Yard, obviously. This is the new Diveunder going underneath, and then this is off towards Reading, the Great Western Main Line. You also got the London Underground Central line going past the end of the yard just here. So, just to give you an idea of the scale of the project that we went through, put that up on that screen. It's useful to review the staging diagrams. This is what it looked like at the start of the project. The aim to create space for the Diveunder, which largely went about through here, was to squish the yard northwards. So we had to compress the yard upwards. As we went through, little bit by little bit, we took out bits. We started relaying the junction at the end here. You can see we're moving all the tracks northwards. There's a new headshunt went in there. Remember that. I'll come back to that in a bit as well. Take out the link at the end. New S&C going in, little bit by little bit. As we go through our stages, all the yard is being moved. This is a new fuel depot. We have to rebuild all their fueling facilities because we move those north. Rebuild it, move north, move little bit by little bit. So you can see what we're doing is creating an empty set of space here. Now, this is a new double junction. We put a whole brand new double junction in for this. These are the poplar lines. These go past the yard, and as I said, they go up to the North London line. This new double junction rejoins the North London line, the poplar lines on much closer to London. That emptied this space, and then that enabled us to take all of these tracks out as well. And what that gave us was a nice big empty space here to start building the Diveunder. This is the main section of the Diveunder. This will be the intersection bridge where the access to the yard will eventually be. This is one part of the Diveunder, and we've started all our piling and our excavation work through there. As we remodeled, this is overhead line changes. So this is all different overlay gantries and things you're seeing on this stage. We get to a stage, we built the top of the Diveunder at ground level. Then we excavated underneath it, put the tracks on top. And then once we've got the tracks on top and we can switch the running over the top of the Diveunder, we can take out this, which is the former access into the yard. And then, of course, that creates space to start excavating the other side of the Diveunder. So it was all done in significant stages. I had to be very careful on the different stages as we went through. A few more overhead line works, then we can bring the poplar lines back in around the back. Now we've got the track going in over the top of the Diveunder, bring that back down, and then we take out the double junction. So that junction lasted about 2.5 years. Brand spanking new double junction going in. 2.5 years, we flame cut it out again. Broke my heart to see the crossings being cut with the flame cutter. I did try and stop them. They told me there was not enough time in the possession to save the crossings, so unfortunately I had to look at lovely condition 2.5-year-old crossings being flame cut, which was an absolute crying shame. But unfortunately, that's sometimes the way of the railway and the possessions that you've got. Carried on moving, a bit more relaying. Now we've cleared that out of the way. Of course, we can extend this end. Extend a bit more of that, and once the double junction was out, that itself was temporary and obstructed the end of the Diveunder. So now that's out of the way, we can carry on building this direction as well. finally get some track in the dive under, we can start relaying the relief lines to join it on at the end. This was Christmas blockade 2015, massive hole in the ground, enormous empty space, all this new S&C going in here. Correct, crossovers going at the end. This is a 90 miles per hour equal split H crossover, and that's a 75 miles per hour crossover at the end. Bit of plain land renewals, and then finally we reconnect temporary connection. And that is what it looked like at the end. So quite a lot of stage works, quite a lot of individual moving around. You also notice at the top some of these stages went out of order because as the project went on, of course, we did change some of the staging around, and we did change some of the order of the stages around, but that's what we got. So before and after, this isn't a perfect before and after, of course. This is some of the works have started, but it gives you an idea of what the yard looked like before we started. Fairly obviously, that's a computer model of what the yard will look like at the end. I said 90 miles per hour dive under, 75 miles per hour out. The only reason it drops to 75 at the very end of the dive under is because we just couldn't get the space for a 90 miles per hour turnout in there. It just didn't work without rebuilding Acton mainline station platforms and moving these tracks up here even further to the north, which would compromise all this and it just became too difficult when we just went out of space. Just to let you know the purpose of the dive under, because it's useful to see it on this picture. The fundamental point is cross-rail trains that are coming on the upper relief, which is this track here. We'll go, sorry, wrong track. On this track here, going into central London, are conflicted by freight trains coming out of Acton Freight Yard on these two tracks and joining on. So the idea is that crossrail trains coming in, or indeed non-crossrail ones into Paddington, can instead go through the dive under, go underneath the access to the freight yard, come back out, and then they can carry on towards London Paddington on the relief line. Doesn't do anything for trains on the down relief, of course. They still need to merge them with freight trains, but all the freight trains going in and out are deconflicted by the ones on the way into London. So, congestion. It's a busy site. This is obviously the dive under going in construction here. You can see these are the two poplar lines. These are the main lines and relief lines over here. This is all the yard going on over here. To get access into there was only a couple of places we could get in there. You only had to climb down sets of steps and move all the materials from a couple of defined access points. It was all hemmed in on all sides. It was all quite narrow. Getting the stuff in the right order in the right place was always a challenge. And there's slightly more overall viewpoint of it. Again, you can see the whole dive under is quite long. It's all at the west end of the site, and then this is Acton Freight Yard up. This is Acton Freight Yard up here. Sorry. This is actually taken from the Network Rail helicopter. Most of you will probably know the Network Rail has their own helicopter. I was very, very privileged to have got to ride in the Network Rail helicopter. I took this photo from the helicopter myself. I was had a wonderful day flying over the site. I managed to wrangle that one. The job does have some perks sometimes. Plenty of room to work in. As I said, it's quite a constrained site. This is the relief lines. This is the poplar lines. Again, it's all just trying to see the size of a digger versus the size of the dive under, trying to get all the plant in the right order. If you find something needs to bypass something else, you've got to go back to the access point, take them both out, swap them around, take them both back in, drive them through the centre of the dive under. It's all quite difficult. And in the early stages, where we only had one half of it built, of course, all plant had to go in and out by cranes. It was all being craned in near the centre and craned back out again. So it was quite difficult if you ever got anything wrong. So, buffer stop risk assessments. As a track engineer, one of the things I do is, of course, when we're putting in a new buffer stop, you have to look at buffer stop risk assessments. This is the upper relief going into towards London Paddington. Trains go in that direction at 90 miles per hour. This is the entrance to the dive under, which trains will eventually go into there at 90 miles per hour. This is London Underground Central Line. So obviously not 90 miles per hour, but a lot of passenger traffic, a lot of very busy London Underground trains on there, an awful lot of risk. And then this is the West End head shunt of the yard. The yard is the busiest aggregates yard in the UK. It sees around 50 odd train movements in or out per day. That's 25 actual trains, obviously. Most of those split the shunt from the reception lines into this head shunt down here towards the bus stop. They then shunt back out into the loading or offloading yards. They then shunt back into the head shunt back into the reception lines. Locos run round, do the other half of the train, moving around. There's an awful lot of movements into that head shunt every day. There's a very, very busy head shunt. A lot of them are fully loaded stone, sand, aggregates, variety of different construction materials. So the buffer stop risk assessment for that was basically maxed out everything. It was quite a phenomenal high score. It was we have to have a head shunt there, we have to have a buffer stop there, but if things go wrong, it's quite mad. So this is our solution. worked with H.J. Skelton. This is a railway supplied buffer stop. Hydraulic rams on the actual buffer stop itself. These on the back here are grills, so there's rails embedded down into the concrete here. This whole thing slides along rails. If the train did hit this, these are just cover grills, so they would just push up out the way, and the whole thing would slide backwards. There's several rails underneath with strong clamps on there, so massive retardation force. These are rails, so if anything derails on the approach, it will still hit the buffer stop and still come to a controlled stop. You can see quite how close the London Underground Central line is just behind you there. It was so big it got its own name. It was called Marjorie. It's not me that named it. It was a guy called Martin Veal, who I believe is actually listening to me on the call, so shout out to Martin. He came up with the name, never quite sure why, but that's Martin for you, for those that know him. At the east end, the East Headshunt buffer stop, this was an early job. It was supposedly an easy job. This is what it looked like at the start. That's what it looked like at the end. Supposedly, that was a nice, easy job to just clear it out, put a buffer stop in at the end, and it was a good way to get started. That was the buffer stop the headshunt I mentioned at the start when I showed you the staging diagrams. But history, of course, gets in the way of these things. This is the old signal box that controlled Acton Yard. Again, Martin was on the project when this happened, but the number of cables, pipes, signal rodding, point rodding things that were dug up there made that supposedly easy job a much, much harder job. So lesson there, I suppose, is understanding what came before, understanding the history of your site, and understanding that the railway always throws you unexpected challenges. It's always quite fun to find what the railway is going to throw at you next. This is the entrance alignment of the dive under itself. It's a 1 in 40 downhill and a 1 in 50 back up again. It's not quite the steepest in the country, of course. Crossrail tunnels, when they finally open, will have a 1 in 26. But obviously that's dedicated rolling stock. That's only restricted. That's purely the Crossrail trains and in a very constrained alignment. Now this is built for Crossrail, but it's not only restricted to Crossrail. So this will have potentially freight trains going through it, all manner of different freight trains. We did do some work on what was allowed through, and most things are allowed through it. But you can see the geometry. You can see the vertical geometry on there. It's quite a sweet one. Coming back up the other side, as I said, 1 in 50 back up the other side. It's got reverse transitions in there as well. Come up, meet the up relief at the other end. Great fun. These are 1 meter lines, and these are 10 meter lines, or 10 meter lines in that direction. So very, very steep alignment. And that's what it looks like on the computer model. Now this is our signal sighting model. There is a signal in the dive under, SN190. You can just see it. That's mapped on the right-hand side of the track. You can see the track is curved around to the left, signal's on the right. You just have enough sighting on there. That signal cannot show a red aspect except in an emergency. Because of the steep gradients, it was decided that stopping trains in there as a normal thing would not be a good idea. So until that's showing a proceed aspect, you can't be signalled into the dive under. So that will only ever show red in an emergency. And then to show the reality, that's what it looks like in reality. Again, you can see the lovely curve on here as it comes out the end. We've taken slightly earlier in the project, but you can see the nice curvature in the signal sighting model do work. So in the early stages of the project, you have to work out, are you going to go for ballasted track? Are you going to go for slab track? What's the pros and cons of the different choices that you want to make? So the geometry, as I said, 90 miles per hour, 75 miles per hour just for the X, 1 in exit, 1 in 40 down, 4.58% G vertical curve in the middle of it, and 1 in 50 back up. Horizontal transitions, for instance, vertical curves, reverse curves. It's not an easy alignment to build. So your first thing is, I need fairly high accuracy, or I need a reasonable amount of space to allow this track to move around and keep the maintenance up. Construction depth is a big issue as well, because of course this is a concrete box. Now, if I put ballast on a concrete box, I need either a fairly deep amount of ballast, or I need to look heavily into things like ballast mats, controlling the stiffness, controlling the settlement, controlling the future renewal of that ballast is, again, a strong consideration. So ideally, in a concrete box, I want to make my track out of concrete, just because it makes the design an awful lot easier. Concrete is, of course, shallower, so you have a much lower dig depth. If I did put ballast in there, because I'd need deeper ballast, the whole dive under excavations need to get deeper. That has potentially quite a significant cost implication. The track alignment, the bottom of the track alignment, sorry, gets deeper. That's more materials to dig out. That's potentially slightly deeper piles. It changes the whole construction methodology. So going for slab track system, which is shallower, actually helps the overall construction. And then obviously ballast degradation. As ballast degrades, if you've got ballast sitting on a concrete base, that creates attrition. That ballast is going to break down and form fines as it goes. So that's the reason for choosing Slab Track primarily. When you decide to do Slab Track, you then have a variety of different Slab Track systems that you can choose. Considerations for which type of Slab Track you use included constructability is the big one. This is a greenfield site, or brownfield site, I suppose, but we're not doing this in a possession. We're not doing this in a hurry. We want high accuracy. We've got steep forces, we've got braking forces. When trains do when trains do inevitably slow down or speed up in the dive under, which they're going to do, they will put strong forces into the rails. We want something that's got nice and strong. We want something that's got good load distribution, good force resistance, and is easy to install. The type of fastening is quite important as well. The Slab Track system that was a product approved at the time had a Vossloh fastening. Now, most maintainers like a standardized clip in a large area. If they can keep the same clip over a large area, it makes their job easier. It's less tools to carry, it's less spares to carry. The fast clip is a fairly standard new clip, and most new railways built on fast clip or one of those types. The Vossloh is a bit unusual. However, in Paddington Station, the Vossloh clips were already present as part of the Slab Track system there. So us looking at the Vossloh system, putting that in, was less problematic. We did talk to the RAN team at the time, and we did say, yeah, we're going to go down this road. Is that a big issue? And they said, no, we've already got the spares, we've already got the tools, we already understand this type of clip. So yeah, fine, back on. So we stuck with what was already approved and already well understood, rather than going for the fast clip system, which there is an option for fast clip on the Rheda 2000 system, which is the one we initially chose, but it was not product approved and not as well understood. Things like welding and managing defects, of course. This is a Slab Track system that's poured in situ, the Rheda system we went with. One of the constraints you've got is, of course, how high up do you pour your concrete? If you pour the concrete too close to the bottom of the rail, you then hit a point where a standard weld mold, a standard emergency clamp, something like that might not fit. So one of the real strong considerations was, do we have enough gap underneath the rail? And to make sure you've got enough gap under the rail for a normal weld mold, a normal emergency clamp, but also have enough cover for the concrete rebar, we had to carefully control those levels. It all worked, but it's just something we need to think about. And of course, settlement transition zones. This is a Slab Track system. Outside, it's a ballasted track system. So the maintainability of the transition zones was a really, really big consideration when we went through. When we started working out what our transitions looked like at 90 miles per hour into a Slab Track system, with potentially difficult geometry coming out. So at 75 miles per hour coming out, having gone through that geometry, your trains are not going to be running perfectly smoothly. So again, thinking about how your transitions settle, how they're going to behave, is quite important. Think about rail wear, RCF, rail creep, pad stiffness. Pads are going to degrade over time. It's a lump of plastic, sort of rubberized plastic. It's going to change over time, and they get stiffer as they degrade. This is going to sit there for a large number of years. So again, just considering how pad stiffness is relevant and how much you use pad stiffness as a factor in your management of track stiffness overall. Again, you have to think, when it degrades, is my overall system going to be different in any way? Is it going to be compromised? So just little things to consider. And of course, you've got the signal in the dive under. So different systems that we considered: resilient base plate, embedded rail, booted sleeper, cast in. We went for the cast in. It's the Rheda 2000 system. It's a prefabricated type of sleeper. This is the rebar. We didn't need the hydraulically bonded layer or the cross protection layers on subsoil because it's not on subsoil. So all of these layers disappeared. It's literally this top section here poured into a concrete base. The dive under was built out of concrete. So this is the sleeper. It comes in. This rebar is part of the precast sleeper that is brought in. That's put in. We thread longitudinal rebar in there to put it in the right place. We set the track into the correct position. I'll show you how in a bit. And then we pour all this concrete around it, in situ concrete pour, and lock the whole lot together into one nice solid concrete lump. That's the fundamentals of a Rheda system. One of the questions we asked Rheda when we were going through the design was, this is going to be on a 1 in 50 gradient. So in terms of pouring concrete and in terms of the forces that this concrete system is going to have to resist, is there an example you can give us of where a Rheda 2000 system has been used elsewhere on a fairly steep gradient? They sent us this picture. I think we all looked at that and went, yeah, okay, that's probably going to work. It was fairly convincing. They didn't actually tell us, or I certainly can't remember what the actual gradient there is, but it says it's been used on a variety of fairly extreme environments, and therefore, yeah, they're quite happy to support a 1 in 50 gradient, no problem at all. It was worth asking the question. So, looking at constructability then, as I said, 1 in 40 down, 1 in 50 up, we had a construction accuracy of plus or minus 2 millimeters. Because on a ballasted track system, in a worst case, if you get it a bit wrong, you can send the tampers out again. If you get it really, really wrong, you can dig the thing up again and you can lower it back down. In a concrete system, if you get that wrong, you are quite literally set it in concrete for the next 40, 50, 60 odd years. It's very, very hard to go back and start breaking concrete slabs out if you get your alignment wrong and you get some faults in geometry. So because we are quite literally setting this in concrete, we knew it had to be pretty much spot on. 2 millimeters is perfectly achievable. We did achieve it. The whole dive under is within plus or minus 2 millimeters. That's horizontally and vertically. Literally do the little circle around the design alignment. The whole dive under is within 2 millimeters of the design alignment. It was really, really good. I believe I've looked at track quality details recently, and they're running really well as well now. There's very little issues with it in terms of track performance, at least. Maintainability, as I said, we looked at the Bosco systems. They've been used in Paddington, castings. I've gone through all that already. And of course, the track slab, the base slab integrity. We've got the base slab, which is the concrete that's been poured as part of the overall dive under structure. We then have the track slab, which is part of the Rheda system, on a steep gradient being poured at a separate time. So they are separate slabs, and they're not necessarily going to have a really strong bond between the two. So we did have little dowels that stuck up from the base slab concrete, and then we poured the slab track concrete on to the top of that as well. So little vertical dowels just sticking up. So again, it was just a force transfer between the slab track system and the base slab of the dive under itself. Thinking about drainage, of course, as well. It's very easy to think of the obvious drainage, which is down into the bottom of the dive under, but drainage sideways on the track as well. We put a fall on the top of the slab to ensure water falls sideways. There's gullies down the side. We wanted it to run off to the drainage channels on the side and not down along the forefoot, because otherwise that would get very, very wet. And then we get lots of stuff growing. Not entirely sure that's worked quite so well, but that was the design idea behind it. So this is a typical cross section, just so you can see. This is at depth. This is the one on the right is the bottom. So this is your drainage channels in the middle. The drainage channels obviously run to the bottom. You have one cross section here, and then there's a big pipe that goes sideways to a drainage chamber, separate drainage chamber, where it's all pumped out separately. And then obviously part of the way down, we have the piles on the side. There's quite a lot of space in there. So gauging in terms of track clearances, structural clearances, window boxes, there's no problems with that. There's plenty of space in here. This is a maintenance walkway. So whilst in terms of sighting, you couldn't work red zone down there and get proper warning, you can still walk down there. There is enough space to stand there safely whilst trains passing. I don't think I'd want to do it, but you could if you really wanted to. And of course, it's overhead electrified as well. In terms of construction, it's a 730-metre long section of slab track. You have going through the track transition ballasted box, which is on the one end, the first box here. You then have a reinforced concrete trough. It's a raft system. So we have literally dug a hole in the ground, we have poured the concrete in, and we've built it up in situ. In the middle section, we have 475 metres of pile section. So you can see here, this section here is piled, and then this is just a raft that's been put in the hole. The water table is fairly high at Acton. As we get deeper, the uplift effect of the sort of flotation effect becomes extremely high. So the piles, I can't remember how deep they went. They went very deep, but they are partly they are all about holding the track down, holding the structure down in the ground and resisting the flotation loads. Reinforced concrete trough coming back the other side, and then a track transition ballasted box on the other side of that. Now, this is a shear connector. When you look at the construction, I'm going to go back a slide there, because the pile section here, that's not going to move. That's attached to very deep piles. You know that's going to stay where you put it. This is a trough that's dug into the ground. We dug a hole, we built the concrete in, so we built the formwork in the hole, we poured concrete in situ, let it set, and that's sitting there largely unsupported. So one of the potential issues we've got is this going to settle at the same rate as this? The pile section is going to settle at, ideally, nothing. this might settle a little bit, and therefore we've potentially got a hinge or a little bump coming off the end of the piling section. These are quite sizable structures. We put those in to join the pile section and the reinforced concrete trough section, so that if we do get any settlement, that will act essentially as a connection, that will act as a hinge here, and therefore the gap, the settlement here, which should be 0, and the settlement here should be 0, and the settlement over here will be a few millimeters something, and the whole lot will act as a simple pivot going that way. So the whole system overall will very gently settle, and the overall alignment that the rails see and the trains see will still be very, very smooth. So we put those in at both ends to keep the lot together. At the other end of the pile section, we then had a change between the reinforced concrete trough, which I was just mentioning, and another concrete trough, which was much shallower and had ballast in it for part of the transition. Because this is now mostly at ground level, again, the idea is the settlement here and the settlement here should be more or less the same. But this is the concrete trough. This is the concrete trough with ballast. They are going to settle at slightly different rates. They are, again, different structures that we are joined together, but we don't want any different here at the rails. So these are much smaller dowels. We didn't need massive structural joints here. These are little stainless steel dowels going between the two, again, just to make sure that the two settle at about the same rate and we don't get any horrible bumps up at rail level. When we were going through the design process, we talked to STE, as it was, Safety Technical and Engineering up at HQ, and they provided us with this. This is a draft slab track standard. This didn't turn up in the final standard, but this was one of the early drafts they gave us. And they said this is their current thinking on platform on their design of transitions between slab track and ballasted track. We looked at that and thought, for 90 miles per hour with this geometry and these alignments, we don't really like it. We thought long and hard about it, and we've incorporated some elements of that, but we took that design, and between Network Rail and the design organisations, which I'll come on to, we've had 2 of them, we've developed that into a slightly more robust, what we think at least, slab track to ballasted track transition. So the concept of the transitions was done on steps, rather than having a gradual change. Some of which is a gradual change and some of which is just a simple step. So we start in the slab track, we then go from the slab track into a ballasted trough that has a ballast mat. The same trough, we have a second ballast mat that's a bit stiffer, and then we have a granular wedge which is built up at the end. So I'll run you through those. This is the ballasted trough. It is on cant, 40 millimeters of cant running at 90 miles per hour. It's got a radius through it as well, just to make our lives even harder. It's a ballasted trough. Obviously, there's drainage, little drainage weep hole coming out the end because you don't want it filling with water. The idea there is to constrain the settlement of the ballast. Now, when you look at how ballast settles, and you look at how track settles, part of it is because the stuff underneath the ballast layer, the subgraded formation, the clays, the sands, whatever it is down here, is settling and going down and settling in a non-uniform manner. On here, this is concrete. This isn't going to settle. But however, the ballast still is going to settle. But what normally happens is the ballast goes in a circular manner. So this will go down, it will push sideways, and then that'll be pushing the shoulders upwards. And that's where some of the settlement comes from. So if we can constrain and control that, then we can create a controlled transition environment. So as we come off the slab track, which is this end, it's 3.3 meters wide. At the other end, it's 3.9 meters wide. So here we're allowing a bit more ballast on the side, a bit wider shoulder, and allowing that settlement to happen at a slightly better, slightly faster rate. And therefore the track here is going to settle a little bit more than the track here. We also go straight from from slab track into a 300 millimeter full depth ballast. Some of our thinking was, well, we should have shallow ballast at the start and we should gradually ramp the depth of ballast up. But the idea behind the 300 mil was you can tamp it, or you can, in the very last bit, you can bring your tampers very close. You've only got the last few to do with manual cargo packing. You don't have shallow ballast that's harder to control, harder to predict. You have fully maintainable ballast, a fully maintainable system with, as best as we could, standard track equipment and standard track tools to come right the way up to the slab track. And therefore it makes the life of maintainer, hopefully, an awful lot easier. That's the idea. Going from the slab, as I said, we had a ballasted trough. These are the 2 ballast mats. So we've got a 10 meter long ballast mat there, 10 meter long ballast mat on the side, 300 mil ballast through the lot, and then coming on the end here, we go onto a granular wedge. So you can see this concrete trough ends here, and then we go on to the next one. That's the end of the concrete trough. We have a granular wedge after that. So this previous one was the 3.3 metre wide here, 3.9 metre wide there. Standard ballast depth, 300 mil throughout, 2 separate stiffness of ballast mat through there. Out the end of that, we have granular wedge. So again, the idea being a nice big thick granular wedge provides a really good level of support. That's going to settle, but it's going to settle by a lot less than something over here, which is going to settle a bit more. Then we extend that out a few more meters, and then we go back down to completely normal ballast. So it's all about little changes, gradually change the track stiffness between the slab track system and the ballasted system at the end. Drainage is a really important consideration as well. So the granular wedge at the end, a wet aggregate fill is going to behave very differently to a dry granular fill. So draining that granular wedge is really important. Unfortunately, due to the levels of the drainage system in the yard and also the level of the water table, it wasn't possible to easily drain the whole granular wedge. We put a drainage system in probably about 2/3 depth on that granular wedge, and therefore the majority of it is drained. And again, the water level will stay fairly stable, and therefore the performance of that granular wedge should be fairly stable. If we put it down at full depth, we just have drainage running all the time. We'd be trying to drain the whole local area, so it would be just below the water table. So we didn't really want to do that. But this is the idea. This is the concrete trough, little drainage pipes going up the side, little drainage pipe going along the end, picking up all of that. That then goes off to a catch pit. This catch pit is a much bigger pipe. That's draining the granular wedge, which is just here, and then that goes off to our active drainage system in the yard. Drainage in the dive under itself. These little gully pots at the side, so our slab track system's going in the middle here. Here you can see this is the same gully pot, just on the side here, just on the side here. So we embedded all of that into concrete. This is the section that was filled with the slab track. All the water would run to the side, down into the gully pots, down this pipe, which is now embedded here. We did put a few access chambers in, so catch pit chambers in there to rod it and clean it. All of that would then run down to the centre of the dive under. And in the centre of the dive under, we have this, which is nice big catch pit central chamber catching all the water down at the bottom. Then that goes off to the side. On the side, of course, we have the gully pots, and they're going down there. 6.5 meters on both sides all the way along. 20 litres per second duty, assist and standby pipes, and the idea was no flooding in a 1 in 50 year storm. Any worse than that, and yes, we might get a bit of flooding in the dive under, but the dive under is not the only up relief. We could, in a worst case severe environment, close the dive under, keep Crossrail train on the up relief on the ground level, and the service will still run. Yes, there might be a few conflicts and a few delays, but overall the service isn't going to be completely shut down if the dive under floods. That rising main is connected to a Thames water sewer in the road. This is that road bridge you saw earlier on in some of the photos. So centre of the dive under, the intersection bridge at the bottom, pipe goes over here through a pump, through an attenuation tank, goes up into the water, goes up into the road, and then discharges into a Thames water sewer. For the drainage part, that drainage tank, CAD drawings, PDF drawings are very good, and you can look at them, and it's sometimes easy to lose a sense of scale on these drawings. This is a side profile of the drainage tank that you just saw there. You look at that and think, yeah, it's just a tank. Here's the pipe. Here's the little pipe that's coming in from the dive under. And you look at that and you don't really understand until you see the size of the train. That's the train in the dive under. This is the whole dive under structure. This thing over here is enormous. It's 7.5 meters diameter. It's 9.5 meters deep. 2.1 meters thick concrete at the base below. That's just flotation. That's because the water table, this line here, is the water table in the area. So all of this is essentially below water. Essentially, we built ourselves a boat. So the whole thing is trying to float. All of this concrete is just weight to hold the thing down to enough 2.1 meters thick concrete base. And all of this massive structure, because this is where your pipe comes in, you only get 2 meters of actual depth, useful depth, from the pipe infall to the bottom of the tank. So there's an awful lot of, not wasted space, but just space that you've got to have there to make the system actually work. We used something called TrackX. TrackX is a modelling software. It's a Excel spreadsheet based modelling software that gives you an indication, a not perfect indication, but a fairly good indication of RCF development and rail wear development. So you can model, do I need lubricators? You can model your track radii, your track speeds. You can model the whole of geometry alignment. You can play with different settings, and you can make sure that the track alignment will perform reasonably well. One deficiency of TrackX is unfortunately it does not take account of vertical geometry. So whilst we did run the geometric alignment through TrackX, we couldn't model the vertical alignment. Now, one of the more important, expensive tools is something called Vampire. It's a much more complicated tool. That's a proper finite element model analysis that we could have run. But again, we talked to the teams for that, and they don't take account of vertical geometry either. It's quite rare for alignments to have such a severe vertical geometry as 1 in 40 down, 1 in 50 back up again. And therefore, it's not really been something that's been in much demand. It's mostly the cant choices, the lubrication choices, the track geometry choices. That's the big thing that generates most RCF and railway. So they are in the long term looking at putting that in, but as far as I'm aware, so far, they haven't managed to do it. But the results, some results are better than no results. The results from the TrackX modeling showed it's just going to sit there. It's going to behave itself beautifully. We've got this one little bump at the end. That's the S&C at the end. That's the 75 miles per hour turnout back onto the upper relief at the end. So that's got a slight bump on it. That is going to get a bit of wear on the end of it, but that's understandable. It's set S&C. We knew how it's going to perform. The light RCF, we expect in the S&C at the east end, 6 to 8 years. We're going to have to grind it. Not a big deal. So one of the methods we used to work out is this thing going to work. We talked to Birmingham University. We had someone from Birmingham University that rather usefully did a finite element model of it. Let me run the little model. There we go. What you're seeing here is the actual build-up of the system. So as we go through, you can see this is our granular wedge. We've modelled the granular layer underneath. This is standard track ballast here. You can see how the model's been built up. So we're going from our granular wedge into our concrete ballast filled trough, through our ballast filled trough, and then into the actual slab track system itself. So they produced this video just to show us that they have modelled it. This is how they built their model up. This is what's actually being run, and that's what the system looked like. And so then we can have a look at the actual results of that system. Let me break that. There we go. Now, red generally is bad. So you can see over here, as we go into our granular wedge, you can just see the triangle here. There's quite a lot of red. That's the existing ballasted system. That's how a normal track system works. That's not necessarily too bad, but what we're looking for is not necessarily an immediate disappearing of the bed, because that would actually be a bump. That would be a discontinuity. We're looking for a gradual decrease in the red. So you can see there's some red there. It gets greener, and as you go into the slab track system, we gradually reduce the forces, and we're having a nice gentle transition from quite high forces into quite low forces in the Diveunder, in the slab track system itself in the Diveunder. So through that, we demonstrated that our track geometry choices and indeed our transition designs, which were obviously in multiple stages, multiple steps, were very effective, and we were likely to get pretty good performance at the track. So the Form B, this is a slightly more onerous Form B than would usually be done for any system. We did a lot of work to demonstrate that the fundamental choice of a slab track system versus a ballasted system was accurate. The fundamental choice of the Rheda 2000 system versus the other types of system we could have chosen was the correct choice. And the design of the transition system that we came up with, all the different steps and things, was going to work, was robust, and was a good design. We produced 2 technical reports. You can see that Atkins was our main designer. They produced 2 very big, robust reports. An awful lot of work went into these. They're really, really good reports. We produced a very detailed Form B. A Form B normally is a fairly simple document with some signature boxes. We had extra signature boxes on there. We had more people interested and wanted to sign this off. We put a lot more information into the Form B to demonstrate and link to these other 2 reports, and link to all the extra modelling work, all the extra analysis work that we had done to prove that the slab track system was going to work. And we came up with the idea of something called a collaborative Cat3 check. Now, normally for something like a slab track system, you have to have a Cat3 check, which is where you get a separate design organisation to check your designs. Atkins rather openly admitted in the early stages they didn't necessarily have enough technical expertise to fully do the slab track system and fully understand all the different concepts and all the different, all the different nuances of the design that we were going through. And they put their hands up and said, I'm not sure we're quite where you need us to be. And actually, we looked around the industry, and there's not that many that have really, really good slab track technical knowledge. So what we did, we agreed with HQ. We had partly Atkins and partly, a few years ago, I'm trying to remember the other design consultant we had now. We're in Arabs, I think. We had Arabs, we brought them in as well. And between two different sets of designers agreeing that the solution would work and agreeing the overall methodology, we got two different designers to sign up to overall the solution worked. And from that, we took that up to HQ. There wasn't exactly a check. It was Atkins did the bulk of the work by a long way, but we brought Arabs in several of the meetings. It wasn't just here's my design, pass it over, write your checking comments, here's my comments, come back again, please modify them. It was much more of a collaborative approach. It was much more talking, much more meetings together. We all pulled our ideas, and several of the ideas that came from all sides, Network Rail, Arabs, Atkins, all together, joined together to form the final solution. And there's our final signature. I took it up to the professional head of track, David Godley, as it was at the time, in May 2015, and I got his signature. And therefore the slab track system was signed off, approved, and went into construction. So that's quite a bit about the track slab system, but obviously that sits in the Diveunder itself, and it's useful to understand a bit about the system, the Diveunder structure itself as well. So the piles and the base slab. Now, what you're seeing here, this is obviously the piles on the side of the Diveunder. This is just blinding concrete. This is about 75mm thick blinding concrete. When they first poured this, what they would then do is go and hydro demolish a gap in the side. Then this area here is backfilled with all the rebar and all the base slab concrete. This is what it's starting to look like as it progresses through. This is some of the works going in. Have a closer look at that. This is what we did. As we filled that gap with rebar, we then would tie the rebar in to the rebar of the pile. So as I said, we hydro demolished some of the concrete out here. That would get rid of the concrete, but it didn't damage the steel rebar. So we could then tie the rebar cages together, and then when we poured concrete back in here and filled this all up again, the whole lot became one big monolithic structure. So the piles and the base slab were all nice and integral, all joined together, very, very strong, robust structure, and that resisted the flotation forces, and that provided really, really robust base for the slab track system to sit on top of. Some interesting work in progress photos as we go through. Because we excavated down, we had these temporary props in the middle because this is quite a deep area, so to allow us to get in there and work, we put these props in the middle. So while the concrete was setting and while these overall props on the top were setting, we had temporary props, and that just allowed us to continue. What we did inside the Diveunder as well, these are the piles behind it, but we put a concrete block wall in front of the piles, mostly just for aesthetics, partly for aerodynamics slightly, just made the area look an awful lot better. We built that up on both sides, and that created this lovely looking alignment. So when we got to the end, nice flush walls going down into the middle, and then of course you can see us going on to putting our rails in, getting ready for putting our slab track systems in. And there's some drainage systems as well. That's how we built our drainage gullies at the end. This is what we call the intersection bridge. So this is the access to the yard over the top. This is the relief lines over here, main lines over here. This is obviously the Diveunder going underneath. This is that west end head shunt where the train is shunting back through the different sets of S&C into the reception lines, into the loading yards, and into the offloading yards over here. This is the two main lines that are going to form when we switch over the main access into out of Acton freight yard over the top of the Diveunder. Setting out and preparing then. So how do we get plus or minus 2mm accuracy? This is the clamping system that we used. This is a vertical jack. What you would do, you can see on the bottom here, little couple of lumps of concrete, little metal back, metal down, and then this is a screw. So we would change the screw up and down. We can jack the rails up and down a little bit, and we can tweak those really quite accurately to get the height of the rails. They're on both sides, both rails. We'll tweak them up again so we get the exact count, the exact rail height, absolutely spot on. This was a side bracket, only on one side. So again, there's a screw on that. We would turn the screw, move the track left and right slightly. That would hold the horizontal alignment accurate. These would hold the vertical alignment and the cant accurate. And this is our track measurement trolley, which we would run up and down quite a lot. We went through multiple times. We had a trial slab system, which we built first of all. We created an alignment on that, got used to it. And then when we had the final slab track going in, we would go, as I said, up and down good 3 or 4 times, tweak the jacks constantly until we had plus or minus 2. I think the majority of it, we got ±1 on most of the dive under. They were really, really good with this trolley. It was a really good trolley, really accurate, and we got a brilliant alignment out of it. Now, of course, we're going to pour concrete in here. All this becomes embedded in concrete. So we would grease the screw thread. This piece of metal and all that stays there. That just becomes part of the overall structure. This we would cover in grease, pour the concrete in situ, let it set, and then we can just undo the screw, lift it out, and then we would grout the hole up at the end. So we'd have a little circular hole in the final structure. That's what, if you ever walk through there and you see them, that's what we're there. That's how we used to set up the alignment. Once it's ready, we then pour the concrete. So we pumped concrete from the centre. There was only one place near the centre of the dive under where we could actually get concrete lorries in. We would then run metal concrete pumps from there along the dive under to whichever section we were pouring at a time. These are metal shields that we built up. Now, one of the issues we don't want concrete getting around Roslo fastenings and getting underneath the other packs. If we did, it would be a pain to take the whole system apart, clean all the concrete out. We'd probably never get it completely clean. And then that's a potential minor bump, minor defect, or just a degradation source, and it's just dirt that we don't really want there. So a simple way, we built these metal shrouds. They were put over the top of the rail, they were put over the top of the fastenings. We could then pour the concrete, and yes, some of it did get splashed around. It did make a bit of a mess, but actually, because this was all covered up, it didn't really matter. So that's how we kept our fastenings and things clean while we were pouring. And then, of course, we put it in a little tent because that helps the concrete setting as well. It keeps on the heating, it helps it set. As we poured it, I mentioned earlier our drainage system. So some of it, we had a slight fall from one side of the track to the other. How we managed to get that in terms of troweling, we came up with this simple, I mean, Bam Nuttall were our main contractor. They came up with the simple device. This is just see it says 0 cant on there. So they would use that to sit on the rails. They knew where the cant was. They knew roughly where the surface of the concrete would need to be for a 0 cant alignment. And then they could use that and go along. And they had a really good troweling team. We got a really good finish on that. And you can just see the vertical jack sticking up there. So that's popping out the concrete. That's what's going to come out at the end. And then we had one of those for 40mm cant as well, and we just used the appropriate template as we went through. And that's what the alignment looked like at the end. It looks really good. Walls are finished, nice flat, nice smooth concrete. You can see that the concrete level is finished pretty much in line with the concrete trough at the side. Water will run nice sideways down into there, into the drainage gullies, and then off down into the middle. Stressing. When you have a full alignment, this is a 1 in 40 down and 1 in 50 back up. If you just put your pulling point in the middle and you pull, all you're going to do is lift your rails up out of the vertical curve. So consideration of where to put your rollers and where to put your pulling point, where to actually cut your rails and where to stress, we had to come up with a slightly more detailed stressing plan than we normally would, because we had to avoid the effect of cutting in the middle. We had to make sure that wherever we did cut, wherever we did pull, we were not going to pull the alignment out. And rollers were an interesting one as well. We asked for the rollers on a Boslo system, and the continental suppliers of Boslo basically said, "We don't have rollers." Well, how do you stress it then? They walk along with hammers. They walk along with big rubber mallets. They undo the track, and they'll literally have gangs of men walking along with rubber mallets, bashing the rail to make sure it moves through. They just couldn't quite believe this. So we've now got rollers made, but that was one of the last. Towards the end of the project, and suddenly all these questions came out about where are the rollers? How can we get rollers? And they genuinely didn't exist. The Continentals don't use them. Quite an eye-opener. So, last few slides, some interesting track layouts. We put a double slip in at the end. The point of the yard was to keep the yard operational, but of course we are compressing it down into much less space. We don't like double slips as track people. They have a habit of failing. They are difficult components, small rails and things, but of course we had to. To find the space to get everything to fit, we had to put a brand new double slip in. So it's quite unusual to be designing a brand new double slip and installing that, but that's at the west end of the yard. All traffic uses the west head shunt, and some of the traffic coming in and out of the yard goes over that double slip. Quite a heavily used one as well. So it's quite an important one. Just off the back of that, we had a tandem. So the double slip is just off the end here. This is another set of S&C just off the double slip, and then we have the tandem here. So again, squishing the yards northwards, compressing it all down together. We had to come up with some interesting designs of S&C just to put everything together and make sure it all fitted. This is the crossover from the down relief to the up relief. This is a G crossover, enormous thing, and an F turnout on the side here. Some big crossovers. This was the big Easter blockade where I said there was a huge hole in the ground, and that's what it looked like. That is the biggest Kira crane on the fullest extension. This is the largest loading beam available in the country, and it just worked. It did fit, it did balance. It was very, very close to overbalancing, and we had to be very, very careful how we moved it along and how we handled it. It was very impressive to stand there and take that photo, and it was perilously close, but it did work. It was beautiful to see it going in, and you can actually see, if you look carefully, you can see the whole crane bending with the load, the amount of load that crane is taking. It is designed to take it, that's not a defect or anything, but it was very, very impressive to see. And then the H switch, of course, the entrance to the dive under with a H, that's even bigger than the one you've just seen. There was no way we can install that with a crane, so these are what's called PEM LEMs. These are quite cool things that have a temporary track underneath. These drive it along, drop it down, these then drive out the way, you pull the track out of the way, and then you lower it down in the final location. So we built this up in the yard, drove it out using these when the possession was ready, and then lowered it into place. Last few bits, staging. So at some stage, this is where the poplar lines were going to be. We put the drainage in before we put the tracks in. Some of the backfill, of course, you have to be very careful with the backfill because we know we're going to come along and excavate here and put the track in. But if we backfill too deep with not quite as good track ballast and forget that this is actually going to be a track, sometimes you can end up with mud and things washing down. We did put a few long bits of material in there, and we did have to dig those back out again. One other interesting thing is disruption to yard operations. Now, this is a yard where they do a lot of splitting and joining trains. We have shunters walking around, splitting and joining trains, and they need to climb underneath trains along here. So if all these rails were on a lot of different tracks in the yard, that would obstruct the shunters. So we agreed that on reception 1, all the rails for the yard would be stored on reception 1, which is why there's so many here. That's the yard they didn't use for shunting operations, and therefore we kept it free for shunters. Things like that to consider when you're rebuilding, and just to understand how you're going to affect the landowner. A few other interesting things. I want you to guess the age here. I'll give you a few seconds to have a look, so you can see the lipping coming off the nose here. This was a standard crossing. This wasn't an EH or a caster crossing. This was a fabricated crossing. This is a weld. You can just see there. You can see the amount of lipping coming off the edge there, and again you can see the amount of lipping on the agreed that this was 250 meter radius. The adjustment switch was straight, but it was just off the end of the 250 meter radius, so it was still being affected by it. And then this crossing again was just off the end of that alignment. That's 5 months old. We got some of our design choices wrong. That crossing was replaced by an EDH crossing, so that's an explosive depth hardened crossing, much harder, much more robust. This was slightly over canted, so we reduced the cant on this down to 0, and that solved an awful lot of the lifting issue. So sometimes we do get it wrong. Sometimes some of the early alignments do need to be changed and go back in. Another one to guess the age on. You can see this is a switch rail. The whole top of the rail is cracking off. Now this was a known issue with the RAPW level design. So this isn't the Atkins level design, the local design we did. This is a step higher, the fundamental design in the RAPW level, the HQ issue. They got some of the NR60 designs here. So NR60 with a heavy trailing load now has a known failure mechanism where you do start to get defects like this. Some areas have remedied this partly by changing HP switches. HP will last an awful lot longer, but there's no effective weld repair for it. So once the switch finally does crack, you have to replace your whole switch. On this one, we kept with standard switches. As far as I'm aware, they're still standard switches, but haven't been there for a few years. So actually, you can weld repair this. You can build it back up, but you have to do it more frequently. But that's the current repair mechanism for that. And that is 7 months old. 7 months after installation, Christmas 2013, it was put in July 2014. That issue was. One other interesting thing, on the Christmas 2013 block, we had a power cable that was supplying a drainage pump inside the dive under. Now, BAM Naffle, who are the contractor that did the dive under itself and did all the concreting and everything, they went home over Christmas. They didn't need to work. They were building the dive under, not possession critical. They got out of the way. Carillion were our main contractor for all the track works at the top. So we shut BAM Naffle down and gave the site over to Carillion in their entirety. Somehow, somewhere during the Christmas block, we accidentally severed the power cable that supplied the drainage pump to the dive under. That's about 6 feet deep worth of water. BAM Naffle came back in the early January and turned up on site and right, we have a bit of a problem. By complete fluke, one of the men from BAM Naffle did scuba diving in his spare time. So he said, no problem. He went home, got his scuba diving kit, brought it back to work, kitted himself up, dived in, reconnected all the drainage pipes and get everything working again and drained it all out. Could have been very disruptive if we'd have to call in specialists and things, but he's just like, no, I know this. I'm a scuba diver. I can do this, no problem at all. So we just left him to it, and they sorted it all out wonderfully. It was great. Operational safety then. Other interesting things that you see on the yards. I specified these bollards here. So this is reception 1 at the back here. This is reception 2. This is reception 3. This is the main yard, and then over here you have the mains and reliefs. A bit of an odd thing to put blue bollards there. Purpose of the blue bollards was safety. Sometimes safety can be very big, complicated systems. In the early days, we were looking at flashy lights and alarms and things like that. The fundamental idea is around here, shunters are walking here. It's a 15 miles per hour yard, and then 5 miles per hour when you get over here. Shunters will be walking around there, feeling fairly safe. Trains are going quite slowly. You can see them. They're all being really careful. They're all under cautionary aspects. They're all under sort of general caution, driving around the yard, non-signalled moves. It's a fairly safe, comparatively, environment. This is reception 1. Trains are coming in here off the main line under signalled arrangements. They are expecting to have no one in the way. They will drive in there at 25 miles per hour and come in a bit faster, different arrangements, and therefore that presents a very different risk. So the purpose of the bollards was purely to have a visual reminder to staff that are sitting there in the yard. As you're walking around over here, you're in one mindset of how the yard works. And before you suddenly step over on that and find yourself on reception 1 with a higher speed train under signalled arrangements coming at you instead, you've got a little bollard there. Oh, hang on a minute. Change of risk. Sometimes safety is something as simple as that. Just take a little visual cue, and that's what it's all about. There we go. General features. We had an outer guardrail. We had guardrails over the intersection bridge, partly anti-derailment and partly stiffness. We had a TPWS grid in the middle there. You can see that's a signal. So for that section, I had to design a little section where we put the guardrails on the outside and then flip them back to the inside. So you can see it comes along in the middle, standard guardrails on standard EG427 GR2 sleepers. Flip it to the outside on timbers, catch any derailed wheel, bring it in, take it through the middle, and then going back out the other way. Quite an interesting little piece of bespoke design. Ground frames, we didn't have any ground frames. We had a little local control unit instead. This was basically hiding inside a load cabinet at the end of it. Little seat, a telephone to the shunter and acceptance switches. Very simple setups. And then a few nice finished article photos for you. So this is the double slip. This is the main poplar lines. And that's what it looks like at the end. And that is that. I hope that was interesting. Any questions, fire them on the chat there. I think Jill is going to accommodate the questions. Hopefully that was useful for you. Thank you.
Yeah, thank you very much. Yeah, that was very interesting. So yes, any question, please, for the chat line? Right, question from Stuart. Have you had any feedback from depot staff about the blue bollards?
We talked to the depot staff at the time when we went in. To be honest, the blue bollards were towards the end of the project when we finally commissioned everything, so no, I haven't. We did consult them at the time and we did tell them what it was all about. They seemed quite receptive to the idea. They also seemed quite receptive to the idea of it being a really simple, basic system, rather than, as I said, flashy lights and alarms and systems that would be annoying and probably over time you just get to ignore them. So something as simple as a bollard is always there. It's always a visual cue. It's always a reminder. They were very supportive at the time, but yeah, in terms of feedback of operations afterwards, no, I haven't. Unfortunately, I left the project at that stage, so I've never heard anything more.
Thank you, Phil. Any more questions?
Anyone else got any more questions? I haven't seen anyone else.
No, there's nothing coming through at the moment, Phil.
Phil, it's Nick Ramsden.
Hi, Nick. Yeah.
Thanks for the presentation, mate.
How
long have trains been running? how long have trains been running on it, and are there any how long have trains been running on it, and are there any issues with the rails or any wear that wasn't picked up?
I left the project a few years back now. It did open shortly after I left. So it's been about 3 years. About 3 years now. It's been fully operational. Obviously, Crossrail hasn't quite come to fruition in that time, but that's the idea behind it. I did look at the track geometry traces recently, just as preparation for this talk, actually, and just have a look at how it's performing. The geometry looks pretty good. I haven't heard any bad things. I've heard a few things about other aspects of the design that weren't quite as good or didn't perform quite as well as we thought. But in terms of track design, it seems to be, as far as I'm aware, at least, performing really well. And the track geometry traces seem to back that up. It seems to be sitting there but doing exactly what it's supposed to do really happily.
Okay, thanks for that.
A question from Robin. Do you know the cost of the large buffer stop?
Being perfectly honest, no. I could probably dig that up for you, Rob. I'm sure I've got a cost document buried somewhere in my details. So if you want to, you've got my email, haven't you? So drop me a line. I'm sure I can dig that up for you somewhere. I think I've got that somewhere, but not offhand. No, I don't.
Okay, a question from me and Phil. Through all this, the work that you've done, did you have to create a new ELR, a new line there for the?
No, it was still part of SW2. We created a new track ID for it. It was, I don't know what it was now. But yeah, we changed quite a lot of track IDs as we went through, because particularly the poplar lines, as we relayed them and changed them, we moved their location as well. So we deleted the old poplar lines and moved the new ones. The Diveunder itself got a completely new track ID. But no, the overall ELR is all SWM2.
Okay. Since Martin seems to be on the call, Martin, why Marjorie?
Oh, hey guys. A bit of a sad story. My grandmother died around the time of installation. So it's just a name that passed on to the buffer stop, really.
Ah, see, I didn't know that either. I knew you called it. You told me it was called Marjorie. I didn't actually know why. Awesome.
Yeah, she died just near around the day of installation. So I just it happened at the time started calling it Marjorie because it was just on my mind, and it was such a large thing. We decided to try and name it, so it just sort of came hand in hand.
Interesting. Cool. Thank you.
Thanks, Martin. A question from George. Was there an issue with vertical acceleration of trains when entering and leaving the Diveunder? The gradient changes look quite dramatic.
Vertical acceleration, no. What we did potentially have issues with was we had to look at coupling strength. We had to look at different types of rolling stock, make sure that the actual performance of couplers and some parts of engineering plant and things were suitable. We did go through at one stage. We thought we might have to ban some types of rolling stock. We looked at banning HSTs and things, but we concluded that they were all within limits. We worked with First Great Western quite a bit to work out which types of rolling stock how different types of rolling stock would behave as they went through the Diveunder. We also looked at the dynamic effects of pantograph collecting on such a steep gradient as steep back up again. We did some modelling through SNCF to work out that the pantograph would actually maintain contact through the Diveunder system. Again, that came out positive. That showed that it would work. It was a bit extreme, but it would actually work. In terms of track forces and stuff, yeah, it's quite an extreme alignment, but yeah, it did all work, and it was quite happy. So we got First Great Western buy-in to all of the design choices as well. We did look at freight for that as well. So we're not barring it to freight actually either. I think we had a maximum length of freight train that could reasonably go through it, because if it gets too long, there's too much load to bring back up the 1 in 40 out the other side. But in general, yeah, most trains we eventually determined could go through it quite happily with no problem.
Okay, we've got time probably for one more question.
I do have a quick comment, if that's all right, please, Phil and Gilles.
Yeah, far away.
Yeah, the eastern side, where you mentioned the old signal box, as you say, that was originally supposed to be a really simple installation done at Christmas. Several months beforehand, the DP at the time, Ray Pocock, said that looks too good to be true kind of scenario, and asked to do some excavation to ensure there was nothing underneath. And that uncovered the whole host of wing walls and pipework and other things that were found at the time. So as you quite rightly say, it's one of those things of do your trial pits and your excavations and anything you need to do early, because if we'd have done that on the day like the intention, it would have stopped the job. And it would have put us back about at least 6 to 9 months, maybe even a year or so. So just a good lesson that was taken away from that.
Yeah, so that's very true. That in many occasions, when we fail to do the proper site investigations, we end up with significant impact on project in terms of cost or time as well. Another question just came in. It was going to be the last one. What rail section was used and have any rail defects been detected?
It was NR60. Interestingly, a lot of the S&C, not just the dive under, but all the crossovers, turnouts, and things we put on the main line, on the relief lines as well, were all NR60. All the turnouts into and out of the dive under, obviously NR60. The whole lot was done in NR60. I genuinely don't know about any other rail defects. Stuff we had at the time, obviously in the yard itself on the low speed, we had quite a bit of lipping, but we corrected most of those. Through the dive under itself, I did leave the project before it finally saw a passenger train, so I'm not aware of any defects. As far as I know, it's performing fairly well, but unfortunately, no, I've never found out.
Okay, thank you. I think we're going to close it here. I'd like to thank Phil very much for the presentations and being the guinea pig for the online presentation. So thank you very much, Phil, I think on behalf of everybody. For everybody else, we are very keen to get some feedback on how it went for you. So if you could put some more comments on the chat line, or send us an email on our West of England section email, which is western@pwi.com, I think. It'll be on the invite that you would have had. And on this, sorry, western@pwi.org. Been corrected. Thank you, Kate. And on this, I wish you all a good day and stay safe. See you all. Bye-bye.
Cool. Thank you.
Thank you very much.
Both.